Okay, we're going to continue on here. Chapter 10. We've been talking about energy in this chapter, and we talked mainly about some important processes. Obviously, exothermic, as we talked about, is when we release energy. Endothermic is when we absorb energy. We talked about kind of two ways that sort of energy is displayed. Um, One is delta H, which is a change in enthalpy. And if it's exothermic, you'll end up with a negative value and a positive value if it's an endothermic reaction overall. If it is endothermic. We talked about how to calculate the change in enthalpy. And remember that basically it's a state function, which means that we add it up like we did in those couple examples, all the enthalpy values for our products minus all the enthalpy values for our reactants, as our products is our final state, right? And our reactants is our initial state. We also talked about towards the very end there, specific heat in our equation here. And once again, Q is heat or energy. And that is usually in values of joules or calories. M is mass, which is usually in units of grams. S is specific heat capacity, which has the 3 units of joules per gram per degree Celsius or calories per gram degree Celsius. Remember that they do want you to know by heart the specific heat capacity of liquid water, which again is that 4.184 number joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius. That also, by the way, is the conversion between joules and calories. So once you remember that number, you should also always know that a calorie is basically 4.184 joules as well. Now, the other one here is our change in temperature, and this should be in degrees Celsius. One of the few things in chemistry that actually is left in degrees Celsius, and that's because, again, typically our specific heat capacities are in degrees Celsius, so you actually don't convert to Kelvin. The most important thing that we did talk about, though, is you always want to take the final temperature there minus the initial temperature, because ultimately, as we talked about, that is what's going to determine whether or not you end up with a positive or negative value for Q, as it will be positive, and it will be positive. So again, it's that change in temperature that really will either give you a positive G or positive Q, I guess would be a better letter. Positive Q, which would mean it would be endothermic, or a negative one. And we talked about the idea that as somebody gains energy or absorbs energy, the reflectiveness of that is that the temperature will go up. So the final temperature will be higher than the initial temperature. That will give you your positive value for your delta T. And that's opposite uses energy, we will see in terms of their temperature, they will go down. And that means that their final temperature is lower than their initial temperature. And again, that is what's going to give you that negative sign. So once again, always do that final minus initial. That will kind of do the negative for you if you need to do that. Any questions on any of that stuff there? Yeah. So I think we did look at this last time. Once again, need to know that. Also, the other version of it, which is our calorie version. The other thing that we talked about in water is probably the main one that you should watch out for. It does change in terms of their specific heat capacities depending on the state of it. So if you're dealing with ice or steam, as you can see there in the table, once again, it has a different specific heat capacity than liquid water. Most of the time, it's going to probably be liquid water, but it could be a different state. So make sure that you are using the correct one. And as we talked about last time, the higher the specific heat capacity, right, that essentially means that you got to put more energy in there to see a temperature change occur than something with a smaller specific heat capacity. You'll be able to see the change with a lot less energy sort of put into it. All right, so I think we left off right here at this example. So let's do this example. Determine the amount of energy as heat required to raise the temperature 10 grams of aluminum specific heat capacity 0.89 from 25 to 58 degrees Celsius. Give the answer both in joules and calorie. Take a couple minutes, see what you come up with here. Okay, so let's take a look at this one. Obviously, we're doing specific heat capacity, so we do want to use our equation here. So in this case, we are looking for Q. We do have the mass, which is 10 grams. We do have the specific heat capacity given to us at 0.89 joules per gram per degree Celsius. We have our initial temperature, 25 degrees Celsius, and we have our final temperature there of 58 degrees Celsius. So we really have everything we need just to plug into our equation here. So we'll put our values in. That'll be 10 grams. 0.89 joules per gram per degree Celsius. Once again, taking our final temperature minus our initial temperature here. And if we put all that into our calculator here, 10 times 0.89 times the difference there of 58 minus 25. Looks like we end up with 293.7. In terms of the units, the grams will cancel, the Celsius will cancel. That leaves us just joules that are left over as a unit of energy. Now, in terms of sig figs here, looks like maybe we got 3 there. I got 2 there. And when we take the difference here, it looks like 2. So probably 2 is where we should end up with, which would be something like 290 joules. Any questions on that one there? Endothermic, right? As Q is positive in this case, which is what we see when we look at the temperature. Temperature went up, which means the only way really for that to happen is it has to gain energy for that to occur. Any questions on that one there? All right, so let's take a look at another one. 294 joules of heat is transferred to 10 grams of silver. What is the final temperature of silver if it has a specific heat capacity of 0.24 joules per gram? And I didn't do the calc on the other back and do it. You should probably answer the question. All right, so we will do that calories. 1 calorie is 4.184 joules. So I'll just borrow that there. 4.184 joules, 1 calorie. Joules will cancel, and that's going to get me about 69 calories. Yeah, so that would be good. Probably good answer with all of the question, I suppose. Yes. All right, so obviously that's just the calorie to joule conversion. All right, so take a few moments and see what you come up with on this one. Let's take a look. So once again, obviously we're using our specific heat equation here. So in this case, we do have Q, which is 294 joules. Remember, as we talked about last time, sometimes people will confuse kind of Q and S together. So again, Q has just 1 unit and S has all 3 of those units together. So it's a good way to sort of remember it. We also have the mass, which is 10 grams. We have the initial temperature, which is 25 degrees Celsius. We are looking for a final temperature here. And we do have the specific heat capacity given to us. A couple ways you can do it. You can plug it all in, including the 25 degrees. Or if you want, you could just solve for the change in temperature. And to do so, I'm going to divide that, guys, to the other side. And that will give me the change in temperature is equal to Q divided by MS. Putting in my numbers here, 294 joules divided by 10 grams and 0.24 joules per gram per degree Celsius. The joules will cancel, the grams will cancel, my degree Celsius will flip to the top when I divide, and that's going to give me here 294 divided by 10 divided by 0.24. That's going to give me on the calculator there a 122.5 degrees Celsius. This technically equals our change in temperature. Now, 2 points on this. Personally, the way I would do it is, I know for me, I am not ending my answer there, right? Because that's a change of temperature. I'm going to continue on and use that for another part of the calculation. I am going to kind of keep track maybe of my significant figures which based on this calculation would be 3, 3, and 2, which means really it should end here. I'm personally not going to round the answer at this point because I'm going to use it to continue on. If you needed to maybe give that as an answer, you should probably round it to 120 at this point as per that part of the answer. But once again, that's not really what we're looking for. So I'm going to leave it, and then I'm going to just keep track of the sig figs and round it at the end. Also, really important, what we talked about was the change in temperature. Again, is our final minus our initial, which means in this case, 122.5 degrees Celsius is equal to our final temperature minus 25 degrees Celsius. So this is why it's important to do final minus initial, because we are actually adding this, right? So that we get a higher temperature to the other side. And that's going to give me, when I add that to the other side, about 147.5 degrees Celsius. At this point, I can now really kind of clean up the sig figs. So once again, this technically should have been here, which really should have been like 120, which means the last thing I did was add in this case, which is 120 with no decimal places and 25 also with no decimal places, which means my final answer here should actually go to no decimal places. And like a 148 probably would be the sufficient answer. Once again, that will give you probably really close to what it should be and rounding correctly. If you did round at 120 off of the first calculation, then obviously you'll end up at 1. Sort of where you should continue on, kind of avoid the rounding until the end, but keep track of it. Any questions on that there? Okay. Then let's talk about specific heat, and a very common way that we can figure out certain things. And it's going to be basically like the experiment you're going to essentially what you're going to do today in lab, and it will help us with the next calculation. So let's say you took a piece of metal like you're going to do, except you'll have a bunch of pieces of metal. And we have this piece of metal, and let's just say, for example, we had a mass of it of, I don't know, we'll go 65.5 grams. And let's just say that we initially heated this metal up to, we'll go 82.0 degrees Celsius. And let's say we have some water over here. You'll have it in styrofoam cups. And we'll just put some water over here in a beaker. And let's just say we had, in terms of this water, about 125 grams of water. And let's just say the initial temperature of the water was 28.0 degrees Celsius. Now, when I take this hot piece of water, a hot piece of metal, like you're going to do, and dump it into my water, as we talked about last time, what's going to happen to the temperature of the water? Will it go up or down? Should go up, because the metal is much hotter than the water, right? So in terms of the metal, it is a exothermic or endothermic process? It is an exothermic process in terms of the metal, right? It's going to give off all that heat to the water, which means the water is an endothermic process, right? It's going to pick up all that heat and energy. The result of that is we should see, as you just mentioned, the water's temperature should rise, like you will see later on. And we'll just say, hey, it rose to 31 degrees Celsius, for example. Now, we also always know the specific heat capacity of liquid water, which is that 4.184 number. The other thing that we also talked about, right, is as that metal goes for a swim there in the water, it will eventually come to what temperature? The same temperature as the water, right? Because it's sitting in the water. So eventually it will release all that energy. When we do figure out sort of the final temperature of the water in this type of situation, frankly, it's sitting in that cup. We know that about the metal. So the specific heat capacity of the metal. So We can use our specific heat equation to help us do that. And we basically have our specific heat equation we can use for the water. And we also could have one that we use for the metal. Now, when we look at the water, we pretty much have all the information we need. We got the mass, we got specific heat capacity, we have the change in temperature, which means just by monitoring the temperature change of the water, we can vary how much energy the water absorbed in that case. If we look at the metal, though, right, that is released by the metal. So because we could figure out how much energy was absorbed by the water, we know that that should be the exact amount of energy that was lost by the metal, as the metal is the only thing that went for a swim, and it should be the only thing that will cause that temperature change to occur basically in the water. So this is a very common process like you will do. You basically just monitor the water's temperature change. We now can just simply use our specific heat equation here to first figure out how much energy the water absorbed. So let's do that here in my made up numbers, see how bad I did. We got 125 grams. We got our specific heat here. Obviously, this is the water, 4.184 joules per gram per degree Celsius. We're going to do our final minus our initial. And in this case here, so we got that and that. So 1569 looks like. 1569 joules. It's a positive number, which makes sense, as that again is endothermic for the water, picked up all that heat and energy. Once again, I'm going to actually continue on with this number, so I'm not going to round at this particular point. But if we keep a track of what we are looking at, we got about 3 there, right? We got about 4 there. When we subtract this, that is 3.0, not just 3, right? Because of the decimal points there. So we go to the first decimal point. So that would be 2, which means technically speaking, if we did need to give an answer for how much energy properly with the sig figs for the water being absorbed, we really should get about 1600 joules. But once again, I'm not going to round because I'm going to use that number to sort of continue on. Any questions on that so far? So as we talked about, all the energy that that water gained had to come from the metal. And it is exothermic, as we talked about in terms of the metal, endothermic for our water, which means there's a nice relationship of the Q of the water will equal negative Q of the metal. It should be the exact same value of energy that came off of the metal than the water absorbed. The only difference is actually the sign, because one is exothermic, right? And one is endothermic. So the metal's Q in this case actually should be negative 1569 joules on the non-rounded number. Should be again the exact same number, just the opposite side to indicate that it is exothermic there for the metal. Any questions on that? So we're using our water to sort of back figure out how much energy was lost by the metal, because we could very simply do that by following the temperature change in the water. And that's how you could do it today in cups. They're very well insulated, no outside heat or energy coming in. How much energy is being given off or absorbed in a reaction. Like in this particular example, we could do something where we throw a solid into water. We could actually take 2 solutions like hydrochloric acid, for example, sodium hydroxide. They're both aqueous solutions, which means they're water-based. You can actually pour them together in your styrofoam cups, throw a thermometer in there, follow the change in temperature. You could use still the specific heat of water, because water is the major component of that aqueous part in most cases. And you could actually figure out how much energy would be released or absorbed through that actual chemical reaction that's taking place by just simply using a thermometer. So sometimes people think you need like really fancy pieces of equipment. A lot of times in terms of energy, a thermometer is kind of all you need, and some nice insulated thing like some coffee cups, and can really figure out how much energy is happening in certain types of reactions. So back to our sort of problem here, we do want to figure out the specific heat capacity of the metal. By using that relationship with the water, we now have the missing piece that we needed in terms of the metal to figure out the specific heat capacity of the metal. For the metal here, we could solve for S. And once again, we're going to take these two guys and divide it to the other side. That will give us Q of the metal divided by the mass and the change in temperature. Putting in our values, negative 1569 joules. Our mass of the metal, 65.5 grams. And our change in temperature, the other important thing, once again, is final minus initial here. So our final temperature is actually 31.0 minus our initial, which is 82.0. That's going to give us what type of number? Bless you. It's going to give us a negative number, right? And that negative number is going to go well with this negative number here to make sure that we do end up with a positive number for our specific heat capacity, which is what you need. So again, important to always do that final minus initial. So taking our number here, 1569 divided by 65.5 divided by the difference there, 31 minus 82. Going to give us something like 0.47. Units do not cancel, so they all stay there. Joules per gram per degree Celsius. So why did I end up with 2? Coming back to what we were talking about here, that technically should be 2 significant figures. That is 3 significant figures. And when we subtract that, we got about 3 significant figures. So now if this is my final answer, I could clean it all up to the proper number of significant figures, which should be 2 in this case. Any questions on that? So that is a very common way. That is essential calculation. Ways. 2 separate calculations, one for the water, one for the metal. You can use this relationship here, which is when we do transfer energy like a metal into water, the overall heat should be 0. But this is sometimes inhibiting because you do need to move one of these guys to the other side, which will give you your mass of your metal, your specific heat capacity there of your metal, your change in temperature of your metal will equal the mass of the water, the specific heat capacity of the water, and the change in temperature of the water. Now, when you do move it over there, technically you got to incorporate a negative sign. And you can technically put that's what basically down here. But my experience is most people don't distribute them negative correctly. And when they try to kind of set them equal to each other, put it all in there all at once, they usually kind of screw up with a negative sign. So you end up like subtracting when you should be adding and stuff like that. So if you kind of do them as separate calculations, like we just did in that last example, you probably won't run into that error. But technically speaking, sometimes people will just tell you, set them equal to each other, the masses, the specific heat capacities and the change in temperatures, and solve for whatever you're missing. But if you don't do that negative correctly, you will get the wrong answer. All right, so why don't you try one here? 110 gram sample of a metal goes for a swim, and 150 milliliters of water. It gets the water from 23 degrees to 25.5. What is the specific heat capacity of the metal in joules per gram per degree? Take a look at this here. So this is pretty much the same situation that we just talked about. We have a piece of metal here, and we got some information about our metal. We have the mass of it is 110 grams. We have the initial temperature is 55.5 degrees Celsius. We also have some water over here. And in terms of the water here, we do have a volume of 150 milliliters. We do have the initial temperature of the water. We also have the final temperature here of the water. And we are looking for the specific heat capacity over here of our metal. We always know about liquid water, also the specific heat capacity. So again, usually not given to you in a problem, but it's just a number you just gotta know, I suppose. At this point, we also will be able to figure out once this goes for a swim, that the final temperature of the water will also again be our final temperature of our metal, as after it goes in there to the water, it will come to rest at the same temperature as the water will eventually reach. All right, so in terms of this, we could use our sort of equation. Once again, I would recommend doing it separate from each other, doing the water first, since we do have enough information to do that, and then kind of use that to relate over to the metal. Once again, though, we do have to do a little bit of a conversion here because we were not given the mass of the water. We were given the volume. So that might be where something like density would come into play. Another number that you should just know is the density of liquid water is essentially 1 gram per milliliter for liquid water there. That's usually the number that you can use. That means I could take 150 milliliters and use my density here. And I'm going to keep the significant figures that my volume had there because sometimes people will use different values there for the density 1, 1.0, 1.00, and so forth. So now I do have the grams of my water, and now I got everything I need to go into my Q. So my Q here for my water, going to be the mass of the water, which is our 150 grams, our specific heat capacity there for liquid water, our 4.184. Once again, taking our final temperature of 25.5 minus our initial of 23.0 degrees Celsius. Degrees Celsius cancel, grams cancel, leaves us joules. And in this case, 150 times 4.184 times 25.5 minus 23. That's going to give us 1,569 joules. Once again, it is a positive number, which does make sense since the water, again, in this example, is absorbing the energy and endothermic. Once again, here I know I'm going to continue on with that number, so I'm not going to clean it up at this point. But again, where we should probably clean it up to is 4 significant figures there. 4, we get something like a 2.5 when we subtract that number, and that would technically be 2. So once again, we technically should probably end up somewhere around 1,600 joules would be the amount of water here, or the energy that the water absorbed. Any questions on that so far? So this is where we can use that relationship that we talked about, that really Q of water we call negative Q of the metal. So that means, once again, the Q of the metal will be the exact same number, except I'm just going to change the sign to indicate that it is exothermic in this case. And now I have everything I need for the metal to go back into the metals equation. So if we go back into our metals equation here, our Q of the metal will equal our ms delta T. Once again, we're going to solve for this. So we're going to send everybody over here and divide. And that will give us that S of our metal will equal our Q of the metal divided by m delta T. Finally, popping in our numbers here, minus 1,569 joules divided by the mass of the metal, 110 grams. And once again, we want to go final minus initial here to get our proper negative. So 25.5 minus 55.5 degrees Celsius. And if we do all that, 1,569 divided by 110 and divided by 25.5 minus 55.5. 0.48 looks like 0.48 joules per gram per degree Celsius. Once again, that 2 sig figs really come off of this top number, which should be 2 significant figures from our previous calculation. That has 4 significant figures. And when we subtract this, I think we do end up actually with 3 significant figures. So again, 2 kind of based off of the first calculation that we did. Question on that. Once again, this is a very common thing. Pretty much the calculation you're going to do for lab today. Pretty much. Yeah. Any questions on it? Questions on specific heat capacity. Okay, so let us finish up the rest of this stuff here. So let's talk a little about energy and nutrition. I think we covered it a little bit earlier on, but there are different types of calories, which are sometimes considered nutritional calories, and those are with the capital C. And once again, one of the nutritional calories is equal to 1,000 of the little calories, and that's equal to 1 kilocalorie. A calorimeter is a device that's used to determine calories of food. Sometimes we use a bomb calorimeter because basically you set your food on fire inside. And as it is burning, basically you just follow the temperature change of water, basically. And you can figure out how much energy was released from the piece of food. And I would give you how many calories there would be. We also could use a calorimeter like you're going to use today, sometimes referred to as a coffee cup calorimeter, just a bunch of really nicely insulated coffee cup. These type of products, and here's a look at sort of a very isolated sort of apparatus, and that prevents any outside interference of energy coming in, right, to affect the temperature of the water that's inside. So it's got some oxygen, some ignition wires. You spark it, and it sets it on fire. So as your cookie is burning, it's releasing all the heat and energy to the surrounding water. Once again, that water is only going to be affected by the food that's getting burnt. And you could, again, just very simply monitor the temperature change of water, use a specific heat equation, and you can figure out, how many joules that would be, how many calories that would be, and how many nutritional calories that would be. Years ago at law school, they used to let you do an experiment sort of like that. You would take like a soda can and put water in it, take like a Cheeto and set it on fire underneath the soda can, let it burn. So as it was burning, it was heating up the water inside the soda can, and you could figure out how many nutritional calories there was in like your Cheeto or whatever it may be that you were burning. Now, when we talk about sort of nutritional calories, we usually deal with carbohydrates, fats, and proteins. And each of this type of food basically has a caloric value associated with it. And take a look at that. We could use these caloric values and how much carbohydrates, fats, and proteins there are, say, in your food, to figure out how many nutritional calories there are, for example, in a serving. That is how they calculate it on the nutritional labels you find on food, where they say so many calories per serving. If you look at those labels, they'll also list how many carbs, grams of carbs there are, fat, and protein are on there. And you could use each of these caloric values. So carbohydrates is 4 kilocalories per gram, or basically 4 calories per gram. Fat is 9 calories per gram, basically. And protein is 4 kilocalories per gram. So what you would do is take the mass of each of those things, multiply it by its caloric value, add it together, and that is technically how they get that number that you see for like total calories per serving. In my experience, they tend to round down. I would imagine for obvious reasons why they tend to round down when you do the calculation. So if you get like 124 calories, they'll like, that's 120 calories. That's pretty close, and they'll round down. So to show you that calculation, we'll come back to this in just a second. This here. So let's just say we did have 1 ounce of some cereal with some milk, and it contained 22 grams of carbohydrates, 7 grams of fat, and 10 grams of protein. And we want to know how many calories, which is again nutritional calories or kilocalories, we had if we ate 2 servings. So basically what we do is we take our grams of carbohydrates there were and multiply it by the caloric value for carbohydrates. We would then do the same thing for our fat. And from fat, in this case, it would basically contribute about 63 calories, nutritional calories or kilocalories. And for our protein, we would do the same thing here. And that would basically contribute about 40 calories. If we add that all together, that would give us basically how many calories there would be in 1 serving of that food that we just ate, 191. Since I ate 2 servings, we would multiply that by 2, and I took in about 382 kilocalories or nutritional calories in that. So that's again on those kind of nutritional labels, how they sort of calculate, the calories per serving and stuff like that. And it's based on these 3 major groups, usually carbohydrates, fat, and protein. Any questions on that there? Yeah. Now going back to that slide we just skipped there. When we do constant pressure calorimetry, which is essentially what you're going to be doing in a lab, and in most cases, with your coffee cups, and that's sort of your coffee cup setup there. You will have some water in your coffee cup. You will add the hot metal to the coffee cup. And again, just by simply following that change in the temperature of the water, you're able to figure out how much energy was absorbed. You also could, right, if it was a different type of reaction, you could also figure out, for example, how much energy was released. And as I mentioned before, you could actually mix just real reagents together in a coffee cup like that with a thermometer, and you can measure the temperature change, do your specific heat calculation. And when you do this at constant pressure and you calculate Q, that is essentially the same thing as calculating the change in enthalpy for a chemical reaction. So all those enthalpy values and figuring out the change in enthalpy reaction that we sort of did the other day, you could actually do it yourself with a coffee cup, a thermometer, and doing some calculations to figure it out. So here again, the coffee cups are being used because they're well insulated. It prevents, for most part, any type of interference of energy coming in from the outside. So all that temperature change that you see in your water in your experiment or in this reaction is a result of the reaction, or obviously the transfer of heat from the metal to the water. All right, so the last thing we're going to talk about here in this chapter is thermal equations. We're not going to go too deep into it because they sort of took out of this class for good reason, really. Hess's law, which you might book if you read it. Definitely do it when you go to one. And sometimes when we get equations, there's sometimes for thermochemical equations because they have an energy component, and that is the delta H. And as we talked about last time, that is probably the most common way in chemistry that when you get a reaction or equation, they'll give you the delta H value, and you can use that to determine if it is endothermic or endothermic. Number depending on which one it is. Looking at this from solid state to the liquid state, split energy and right, endothermic. This so is positive. This number on another chapter, that is what is actually known as the heat of fusion. And the heat of fusion it's the energy that's required to take substance from solid to liquid or liquid back to solid. That happens, as we might remember, at the same temperature. So something like water, that's 0 degrees Celsius. So at 0 degrees Celsius, there's a certain amount of heat just to take ice at 0 degrees Celsius straight across to liquid water at 0 degrees Celsius, not change the temperature. And you would use something like heat of fusion to calculate that energy. The specific heat equation that we've been using is what we use when we have something that stays in the same state, but the temperature changes. So if you think about the liquid water, it's liquid water all the way through as the temperature changes, but the temperature changes. So that's really what the specific heat equation is used for, to figure out what happens when you have a substance in the same state, but it changes temperature. Something like heat of fusion, heat of vaporization, which we'll talk about in a later chapter as well, is used for those like transition of states, but not changing the temperature. So if we did need to go though from liquid water to solid, that is actually an exothermic process, right? You got to release the energy. And basically, as we went from this equation to this equation, all we products became our reactants. When you reverse a reaction or an equation like this, what happens to the delta H value is it changes sign. So it originally was positive. When we reverse the reaction, it becomes negative. Just like if we started with this equation here and went to this equation, we basically flipped it from a negative to a positive. So if you ever in some situations, like when you get to the next class and you use Hess's law, and you need to flip a reaction around, you basically change the energy by changing the sign of it. So if it was positive, it becomes negative. If it was negative, it becomes positive. Sometimes we're not interested, say, in one water, but maybe we're interested in two waters. So we have to actually multiply that equation by 2 all the way across. How that affects the energy is we multiply the value, the delta H, by 2 as well. If you had to multiply by 3, you would multiply by 3, multiply by 4, multiply by the energy by 4, gives us this. So if you had to multiply by a common number, we multiply the delta H by that common number. And last sort of rearranging would be, if I went from this equation back to the original equation, I essentially divided by 2 all the way across to get 1 of everybody. And the delta H would be divided by 2. So you would divide by 2. So those are a few common ways that you have to manipulate an equation. If you reverse it, the delta H value sign changes. If you have to multiply the equation by a common number, you multiply the delta H by that number. And if you have to divide by a common number, you divide the delta H by that number as well. Any questions on that?